Good morning, everyone. So I find myself in a new and different business called Titles as a Service. When I submitted my abstract in April to OpenNebula, this was the title, and this is what my project was called at the time, the Fermilab Virtual Facility. Within days after I submitted that abstract, the project got renamed to call the Fermilab 1 Facility. And before June, the project was again renamed to the FermiCloud facility. And that is what it has stayed for 4 or 5 months now. They haven't renamed it again yet. Now we have enough documentation, it would be hard to rename this. So I'm Timm, I'm from Fermilab, and I am now the technical advisor to this project, which is a new project that just started this year. Previously, I was the lead of the FermiCloud project, and I will go briefly over that, how we got involved with OpenNebula, and how we continue to use it, and then, more importantly, our motivation for expanding to commercial clouds, the goals of our FermiCloud project, our use cases, our architecture, and significant developments thus far. So the FermiCloud project began in 2010 with me as the technical lead. At that time, the data costs to commercial clouds were considered prohibitive, so our boss said focus on the private cloud. Our first OpenNebula was installed in November of 2010. That was version 2.0. It quickly grew to be our only cloud system. We contributed the X509 authentication modules for OpenNebula 3 and greater. We're currently running OpenNebula 4.8. We have 29 bare metal hosts for interactive and special purpose VMs, and 280 older 8-core nodes for running batch virtual machines. All that's maintained by 0.2 of an employee, namely myself. OpenNebula developers have always been cooperative throughout our thing. They're always willing to take our patches and features. That's a key reason why we chose and stayed with OpenNebula. Some of the important outcomes of FermiCloud project over the past 5 years. One of the first to publish MPI virtual machines across virtualized InfiniBand. One of the first to deploy X509 authentication authorization. Secrets repository for virtual machines so that you don't have any persistent secrets stored on the VM. They are stored in RAM disk. Extensive discovery of distributed file system performance. Federated cloud using Amazon and OpenNebula, which the rest of this talk is about. Idle virtual machine detection, software development, testbed for 100 gigabit WAN and for IPv6 network efforts, automated image system to serve OpenNebula and AWS, and important testing and integration facility for the Open Science Grid, which is the United States grid thing, and our own middleware developers at Fermilab. But why expand to commercial clouds? So even your best and most efficient internal IaaS doesn't solve key problems for the US R&D agency. You still have to have a computer building. Right now our computer buildings are not full, but they're getting close to full. You still need people to manage the computers. You still have to procure computers on a long government procurement life cycle, which in the US is between 3 and 6 months. I'm told in Europe it can be almost a year for some government institutions to get a tender out. Our US funding agencies are reluctant to build new computing centers. We've had plans on the board for a new one for almost 5 years now. No money is forthcoming, no ground has been broken. Our current one was supposed to have a 12-year life cycle and it's been up for 11 years. Procurement's long and getting longer. Furthermore, our demand is showing a peaking pattern. So our users keep our main cluster full all the time, but there are certain points in the year where things get much more busy than that. Temporary peaks that can go up to 4 and 5 times the demand. So we have one current use case, which I'll go into more detail. It requires 56,000 computing cores for a month. For scale, we have 2 big clusters at Fermilab that are about a quarter of that size. We can't buy machines or build buildings that fast. both because we don't really have the money to buy that many machines, and plus that would more than fill up our building. We expect that the opportunity cycle on the grid will be less available going forward too, although that's not yet true. So in fact, a lot of our users are, part of the way we're surviving now is by leveraging opportunistic grid cycles to a factor that's about equal to what we use at the rest of Fermilab. Most importantly, the users that we serve want to do it and they need the cycles. So this is a major shift within the past year, I would say, that the science experiments at the Large Hadron Collider are all of a sudden decided they have to get behind this. And our own smaller experiments at Fermilab also have decided they really need to get behind this and do this. They do the math and they realize that as a field of high energy physics, we can't buy our way. We can't build our way out of this with computing centers. I'm borrowing a slide here from my colleague Oliver Guchke that shows our, just for the CMS experiment at CERN, what is their demand. And what you see is it's peaking near summer conferences and near winter conferences. Notice they weren't running here for the last year, for the last 2 years, 2013, 2014. They were down. If this graph was pointed up here, we would see a spike as Large Hadron Collider turned on again in the summer, running at twice the energy, twice the data, and a computing problem that goes up as the square of how many tracks that you have. There's the more complex you get, there is a power law going up that it takes the square as long to do. So we need elasticity. Thus comes the Hub Cloud Facility project. So we need to extend our current facility services to transparently run on a mix of resources, commercial and community clouds, grid federations, high-performance computing centers to perform the full spectrum of computing, including data-intensive simulation reconstruction at production scales, local, remote, or both, and allow the facility to respond to peaks without over-provisioning local resources, and make all that transparent to users. So we've been doing a lot of this for a long time. I mean, I've been in the distributed computing game ever since I've been at Fermilab, and that's almost 15 years now. But the new part is who's doing it. So this is not one experiment or one group of users writing some software to go out and say, let's collect from the grid and from the cloud and from local. This is now our facility doing this on behalf of a whole bunch of users. Likewise, adding HPC centers, this is fairly new. There have been tests going on, but not in any organized way. Whenever the difference between Fermilab and some of the bigger computing centers is 2 more zeros on the end of their budget. So we may get a couple $1 million a year to buy hardware. They get $100 million a year, and our funding agency wants to make sure that's very well utilized. So this is a very big push of this new project. And full spectrum of computing, this is also new. So our boss said, okay, you guys picked the easy cases up till now. You were using things that had no input, very little output. Okay, do the hard stuff. Pull your big data to the cloud, run it there, push it back. And then make all of it transparent to users. Well, yeah. Well, the system we had before was sort of transparent to users. This one will also sort of be transparent to users, but not too transparent. And I've lost my button. Oh, there we go. The NOVA experiment at Fermilab, which is a neutrino experiment looking for neutrino oscillations, shooting neutrinos from Fermilab to 1,000 kilometers away in Ash River, Minnesota. And the challenge there is to find the one real neutrino event out of all the background that's out of there. And the computing is basically a lookup table. Say, okay, does it look like this? Does it look like that? Does it look like this? It's a very similar algorithm to what an IBM Watson or an IBM Deep Blue might do, chess playing. So the campaign that we've envisioned data reconstruction, 250 megabytes in, 250 megabytes out times 10,000 times 6 times over. Beam simulation, you have no real data, but you have to take all the information from your simulated beam. So that's actually more data to move, 5 hours per job. So that's expected to be 2.1 million hours. So that's not all of Nova's thing. It's 1/5 of what they did last year, but it's a significant amount. And the goal is to make it reproducible. So, in fact, we did a scaled demonstration of Nova just a year ago, but between that time, their software changed, the people that were running the software changed, and so forth. So this time we want to get it so that I don't need the experimental guru sitting with me every time I do something, or I don't have to sit with him, but their regular guys that submit their jobs can just do it, and at most with one extra flag, say go to the cloud. So also of interest, there's a final stage of this pattern matching that requires 256 gigs of RAM at least to do. If they had more, they would use it. And that's a bottleneck right now because there's only one machine in their whole collaboration that can do that. So we also prototyped that on Amazon Cloud to see how that would work. It worked pretty good, expensive, but it worked. Use case number 2, the CMS experiment at CERN. They started their new high energy run earlier this year. New energy, new beam spot, they have to redo lots of simulation. They need more than 1 billion, but they want to do 1 billion on AWS. And it would take about 4 months to run that at Fermilab's Tier 1, which has 40% of all the CMS computation in the world. So this shows you this is maybe equivalent to 25% or so of all of CMS computing. It's a big chunk for them. Their philosophy is if you can't do it at scale, why do it? And expected it will generate up to 800 terabytes of output data. What is it doing? You're throwing the dice. Did I get a top quark? Did I get a top quark? Oh, there's a top quark. I simulate it. What will it decay into? I digitize it. Okay, what will this look like in my various detectors? And then I reconstruct it. And that's basically like playing connect the dots in 3D. The track will be a spiral in 3D, and then you have to analyze it. We may also add reconstruction of experimental data. It's actually easier to do the whole simulation in Amazon. If you have to do a big transfer in, it's much less computation time, but you're paying for your transfer time if your virtual machine is up while you're reading, or you pay for your S3 if your virtual machine is not up while you're reading. This is our public architecture diagram of the HepCloud facility. So we interact with some virtual organization infrastructure. We present our interface to the outside to look like a computing element that one would use in grid computing. And underneath the covers, the key here is the decision engine, the collector, and the provisioner. So we've always had a provisioner. In our project up to now, that's been known as Glide WMS, but it's a stupid provisioner, and I'll come to more detail there in a minute. The decision engine is what determines how much money to spend and where and how and for whom. Likewise, local computing resources, including FermiCloud, high-performance computing, OSG computing, and cloud computing, public cloud there. Network topology. So this is the first and most important thing designing any cloud, whether public or private. And part of the reason we can do this now, that we couldn't do it 5 years ago, is that our major US research networks have peered with Amazon at peering points close by, up to 100 gigabits in near some of their regions, not 20 near others. Amazon has direct connect, so I could extend my whole Fermilab network into Amazon, and we tried it as a demo. We decided not to do that using just normal internet routing and Amazon Internet Gateway, and using firewall rules to block traffic that's diverging from Fermilab in either direction. High latency requires multiple streams to be used for data transfers. We've demonstrated up to 7 gigabits per second. On 100 gigabit length, that's not perfect, but it's good enough for what we need. The decision engine. So historically, we ask, do you need slots? Okay, go get them. And not really concerned about how much does this cost me to get them. Now we need a smarter algorithm to optimize job location based on cost and completion time. And you burst the public cloud if your local facility is full, and it's likely to stay full. And there's jobs that are technically suited to run on the cloud. And your group has budget and priority to write in the cloud, but try to avoid letting one graduate student burn, 1 minute. Uh-oh. Friendly grid size and HPC, okay. I have 5 minutes because you started late. We have to plan our workflows more carefully. CPU time, stage in time, stage out time. Most importantly, what do you bid? You can get resources available very cheaply, but if someone bids higher than you get preempted. We've had a student doing most of the summer publishing a paper. Most people that do this use very short applications. We don't. We're trying to go longer. Christmas is coming. Amazon needs their computers for what they do. So this is tricky. The main goal I want you to take from this, red is bad. If you bid low, you never start. You get no work done. If you bid maybe 25% of on-demand price, you start 65% of the time, and you pay about 13% of the total cost that it would cost to be on demand. If you bid high, you start every time, but you pay a lot of money. On-demand services, these are using the Amazon stackable services. That'd be a very nice feature to have in OpenNebula. Dynamic DNS, but we've scale tested it both for throughput and for number of requests per minute. Seeing this as Back to the Future Day, a couple slides on where I think the future is going, at least in the US, science labs. The historical grid collaborators are coming up with new ways to go. Aggregating access to cloud and supercomputing centers is going to be hard to beat the economies of scale, even for someone like Fermilab with a huge network pipe and a big computing center and cheap power, which is probably a quarter of what you're paying in Europe. But it's hard to do the real calculation in a way that everybody agrees. In particular, I have not yet convinced my boss of that, so I don't have any real numbers here. Many collaborations will have cloud in the name, but include significant non-cloud activities. There's a big opportunity for those who really needed HPC anyway and didn't have the access to it, and big resource for high throughput computing. Nevertheless, there's still space for open source IaaS at local facilities. It's not an either or, you need both. Flexibility, server provisioning, having computing close to storage is important to us. CERN went all in with the IaaS cloud. I think most of the other places will not do that. I know Fermilab will not do that, and I'm not aware of any other US lab that will or has. In the US, Amazon is dominating for now because they've done the homework of how to sell to the government. There are certain security things that you have to do. They've done, most of their competitors have not done. And the funding agencies will require diversity and open standards eventually, once they figure out what's going on. Good cloud projects start with good policy, good security stance, and good networks. Flexible provisioning is key from expanding from local to grid to cloud to HPC. The longer you have a cloud system, the more people think of new ways to use it and do computing they could not otherwise have done. We've had successful use cases of both of our, successful tests of both of our use cases, and we're ripping up major scale tests now. High energy physics demand for computing cycle is potentially near infinite. We're limited only by our own disorganization, and we need to make use of all possible platforms. And finally, thanks to all these various entities, especially OpenNebula for bringing us here today, but also to Amazon, to Scientific Linux, to Kisti, who funds a lot of our research, R&D development in Korea, and Illinois Institute of Technology, who gets us a lot of graduate students that are very good and get a lot of papers published, and to the NOVA and CMS experiments, also to HT Condor, whose thing can talk to OpenNebula and does, and we use it a lot. And they went to a lot of lengths to make that work. Okay, thank you. Questions?
Is there any question for Steven?
I have one question.
Yes.
You mentioned that in the government area, it's been used the emission infrastructure. I read somewhere that the term community cloud that will be applied for the public cloud used by for the government.
When we say community cloud, there are various research clouds in the United States right now. There's one run by the National Science Foundation. There's another one coming up with the Department of Energy. It's meant to be a cloud that's shared by a community. There's some dispute if it will also include pay for a cloud or not. My understanding of the definition, it doesn't include paid for cloud, that it's that you're sharing on basis of common interest or shared allocation or shared funding. Did that answer your question? Okay.
With the amount of data you need to transport from your private facilities to Amazon,
right.
what would you estimate is the how much % would you pay for transporting the amount of data as in comparison to the using of the exact computing power?
There are limits to what I can say as to what Amazon has actually done for us in terms of giving us a break on that. They do give us a significant break since our research network is bearing all the cost of getting the data in and out of there. So, and they do that. The condition is that it has to be less than 15% of the total cost. And the use cases I've shown here both are less than 15% of the total cost of networking. And for scale, the first use case is $30,000, and the second use case is $300,000.
Thank you, Steven.